Okay, this video is going to finish section 12.1, Intro to Limits. This is day 3, and this will just be this last bullet point here. Use the properties of limits and direct substitution to evaluate a limit. When we're looking at these functions, we're always worried about dividing by 0. Like here, if I pick the value x as 1, if I plug it in, I get 1 squared minus 1, that's a 0. That's not bad. Dividing into 0 is legal. But if I put that same x as 1 down here, I get 1 minus 1 is 0. 0 divided by 0 is extra bad. So this is always what we're worried about when we're looking into these limits. But what we should always try first is to direct substitution. We should just take the number that we're approaching, plug it into the function, and see if a value pops out to see if we can find the limit that way. Now, of course, to make it all official in the math world, we've got to come up with some definitions and theorems and stuff. Just keep in mind as we go through all these basic limit things, all these are doing is just saying try direct substitution first. So the book says, sometimes, as in example 2, the limit of our function as we approach this number c is simply f of c. We take out that x value there, replace it with c, and we get f of c. In such cases, the limit can be evaluated by direct substitution. That is, the limit as x approaches c of f of x, just take the c, plug it in, is f of c. There are many well-behaved functions, such as polynomial functions and rational functions with non-zero denominators that have this property. The list below includes some basic limits. So, let b and c be real numbers. N is a positive integer. The first one here can be probably the most confusing. The limit as x approaches c of b is equal to b. Now it's weird with all just the x's in there, or excuse me, all the different variables in there. But if I wrote something like, let me just change that to the limit as x approaches 2 of 4. So here, this 4 is our function. What does the function 4 look like? Or you could think about it as y equals 4. Well, here's 4 on the y-axis. Y equals 4 would be a horizontal line. So no matter what I am approaching, my limit is always going to be this same value. You know, here, let me just erase some of this. X approaches 2 is 4. The limit as x approaches 2 of 4. Well, here's 2. As I approach 2, you know, here's 1. I'm up here at 4. If I'm at 1.5, I'm up here at 4. If I'm at 1.9, I'm up here at 4. No matter what number I'm approaching, you know, it doesn't matter that this is a 2. This could be a 3 or a 7 or a 15. The limit as we approach any number down here of 4 is just 4. So that's why, you know, we got this as we approach c of b is just b. The limit of a constant is that same constant. The limit as x approaches c of x is c, because we just directly plug that c value in right there, and that's the number, c. If you want to think about it graphically, here's our function, the limit as x approaches c of x. Well, that would be the function y equals x, or just a line going through the origin, slope of 1. So if I put in a 2, I get out a 2. If I put in a 3, I get out a 3. For option number 3, it also works for bases of exponents. X approaches c of x to the nth. We just take that c, plug it in for the x, becomes c to the nth. It also works for radicals. It says here as we approach c of the nth root of x. Well, that c value is just going to take the place of that x and become the nth root of c when c is greater than 0 and n is odd. Remember that odd index there, we can, or when it's even, we can take the square root or the root of a negative. If that is a positive number, the radical must be under an even root. But all these again are just saying direct substitution works. Here's some other properties. Properties of limits. B and C are real numbers. N is a positive integer. But now we have some functions. F of x, as we approach C, has a limit of L. L is just some number. G of x, a different function, as we approach the same number C, has a limit of k. Remember, these L's and k's are just numbers. They're limits. So scalar multiple. If I have the limit as we approach C of this number B times f of x, well, I could sort of mentally just bring that b out front. That limit f of x, that limit is this L here, and then I could just multiply it by the b that I brought out front. B times the number L. Number 2, sum or difference. If I have the limit as I approach C of f of x plus or minus g of x, well, I know the limit of this f of x is equal to this number L. The limit for g of x is this number k, so I would just add or subtract them as needed. You'll hear maybe in calc class, this is the limit of the sum is the sum of the limits. The limit of the sum is the sum of the limits. Number 3, it works with multiplication. Here we have the limit as we approach C of f of x times g of x. Well, the limit of f of x is that number L. The limit of g of x is that number k, so I could just multiply them together, L times k. The limit of the product is the product of the limits. Number 4, quotients. It works with fractions as long as your denominator is non-zero. The limit on our numerator f of x, that limit is L. The limit of g of x, well, that limit's k. So it's just L divided by k. Again, as long as k is not 0. And it works with powers. Here our limit as x approaches C of f of x raised to the nth power. Well, the limit of f of x is just that number L. Raise that number L to the nth power. Always try direct substitution works. Or always try direct substitution. Hopefully it will work. So let's try some out here. Example 9, we've got a through f. The limit as x approaches 4 of x squared. Well, plug the 4 right in there. That becomes 4 squared. 4 squared is 16. Letter B. The limit as x approaches 4 of 5 times x. Well, that 4 is going to jump in, take the place of x. 5 times 4, last I checked, is 20. C. X approaches pi. So our numerator has an x in it. That's going to become a tan of pi. Denominator is x, so that'll turn into a pi. Tangent at pi is 0. And 0 divided by anything is 0. Letter D. X is approaching 9. Our function is root of x. So that 9 jumps in there. For part D, the root of 9 is 3. Letter E. X is approaching pi. X times cos x. So that x, this pi, is going to jump in for that x and that x. So this is going to become pi times the coset pi. What is the coset pi? Negative 1. Negative 1 times pi is negative pi. Letter F, last one. I just write it bigger down here. The limit as x approaches 3 of x plus 4 quantity squared. So the 3 jumps in here. 3 plus 4 is 7, so that becomes a 7 squared. 7 squared is 49. Here's a few for you to try. Pause the video, try them out, start it back up, see what you got. All right, letter A, x approaches 3 of 1/4. Remember, our approach number in a setup like this is irrelevant. Our answer is just 1/4. Letter B, approaching 3 of x cubed. Plug the 3 in. 3 to the third, 27. Here, x is approaching pi, so upstairs is going to be cos of pi, that's a -1, divided by x, which turns into a pi, -1 over pi. Letter D, limit is x approaches 12 of root x, so that's going to jump in there and become a root 12. Now, hopefully you didn't leave it as a root 12. There is a hidden perfect square in there. 12 is 4 times 3. Root of 4, that's going to turn into a 2. 2 roots of 3. Much better. Letter E, pi jumps in for both of those x's. So that's going to become pi times the tangent pi. Tangent pi is -1. -1 times this pi, negative pi. Ooh, excuse me. What am I doing? Tan at tangent pi is 0. Jeez. Tangent pi is 0. 0 times pi is 0. There we go. Here we're going to plug in that 3 for this x. 1 minus 3 is a -2, and that is squared. -2 squared is 4. Limits of polynomials and rational functions. Part 1 here, if p is a polynomial function and c is any real number, then as we approach c of p of x is p of c. This just says direct substitution works on any polynomial. You know, if it's x to the 5th minus 4x cubed plus 7x plus 3. As long as it's just a plain old polynomial, direct substitution will always work. Part 2 says it's always going to work on a rational function as long as your denominator is non-zero. So part 2, r is a rational function. R of x is p of x over q of x. So p of x is our numerator piece. Q of x is our denominator piece. So the limit, as we approach some value c, we would direct sub in. That's going to be p of c over q of c, provided here that q of c is non-zero. We can't be dividing by 0. Other than that, direct substitution will work. So always give it a try, and if you wind up dividing by 0, we might have to try other options. Example 10 here is just, find the limit. Let's try them out. First one is a polynomial, so I know automatically it's going to work. I plug in the -1, so that's going to be a -1 squared plus a -1 for that x, and then minus 6. So -1 squared is 1, plus a -1, that'll be a -1, and then minus 6. 1 minus 1, well, that washes out to 0, so what we're left with is -6. Letter B, x is approaching -1. X cubed minus 5x over x. Always try direct substitution first. So that's going to be a -1 cubed plus a 5 times a -1 over -1. So when we cube, the negative escapes. So this will be a -1 minus 5 divided by -1. Oh, there's my screw up. When I did this negative, because that was a minus, times the -1 here, that was a plus. This should be a plus. My bad. So -1 plus 5, that's 4, divided by -1 is -4. Direct substitution worked as long as we weren't approaching 0. If we were approaching 0, our denominator would be 0, and we'd have to try something else. Letter C, gee, they love putting -1s in these things. Oh, okay, now I see. This, it's the same as what we got here. So that's that same numerator. So that is just going to turn our numerator into, what we get for part A, -6. And when I put this -1 down here in the denominator, -1 plus 3 is 2. So if we divide negative 6 by 2, we get positive 3. And I believe this is the last checkpoint for this section. So try these out after you pause the video and then fire it back up, see if you got them right. First one, plug in a 3. You're going to get a 9 minus. Plug in a 3 here. 3 times 3 is 9. So that's 9 minus 9. That's going to wash out to a 0. So we're just left with 7. See here, we're approaching 3. And this numerator is the same as what we found here. So that numerator is just our 7. And we're approaching 3. So that x turns into a 3. 7/3. Letter C, approaching 3, so upstairs, 3 plus 3, that'll be a 6. And then down here, that'll be a 9. 9 plus 9 is 18. 6 over 18, pull out a 6, we get 1/3. Final answer. So to summarize, now state two cases of the limit concept in calculus. State the definition. Blah, blah, three common types of behavior associated with non-existence. Remember, that is different behavior from the left and the right, unbounded behavior, or oscillating behavior. And then properties and limits, always just try your direct substitution first. Watch out for dividing by 0. The homework for this section. Now, it sort of seems like it might be a lot there, but there's a lot of this is just direct sub. So you're just going to plug in that number and chug and see what it comes out. Or it might ask you about the non-existence. What are the 3 reasons? Or no, I guess that was the last lesson. So this will just be about mostly direct substitution.